The models begin failing before the signal stops behaving. At first, the bursts settle into intervals stable enough for observatories to schedule around. A pulse arrives. Another follows close to the expected window. The charts finally start flattening into something measurable. Then one monitoring run cuts off mid-sequence. Predicted bursts never arrive. The receivers keep searching through empty data for hours, while archived timing overlays remain frozen on the wrong intervals. Weeks later, the source returns from the exact same point in space. The signal survives the corrections. The corrections stop surviving the signal. A thin white spike cuts across the monitor and disappears before anyone in the room finishes reacting to it. The black frequency bands flatten again. No explosion follows. No expanding debris field. Just silence returning like nothing happened. FRB 1210-2 keeps transmitting from the same point. In 2012, the Arecibo Observatory caught the burst arriving from more than 3 billion light-years away. The signal lasted milliseconds, then the source disappeared completely again. Most bursts behave once and disappear. Observatories log the event and move on. Months later, another burst arrived from the exact same location. After that, the monitors stopped getting shut off completely. Long stretches of empty noise filled the speakers, while telescopes remained fixed on a section of deep space that looked completely dead. The signal stayed quiet long enough that astronomers stopped expecting it to return. Then another clean spike appeared without warning. Same region, same spike across the monitor, then silence again. By then, the bursts no longer looked random. Whatever was producing them was still there, continuing somewhere behind the silence, whether anyone understood it or not. The observation schedules start changing before the source does. Teams using the Green Bank telescope begin holding longer monitoring windows on the same region of deep space because the bursts are no longer arriving one at a time. Frequency displays that once stayed mostly empty now fill with white spikes clustered across the screen. One burst appears. Another follows minutes later. Before the tracking systems finish updating, 5 more cut across the screen. FRB 1210-2 never repeats the same way twice. For a while, the arrivals start looking predictable. Detection maps stack over the same location again and again. The intervals narrow enough that people in the control rooms start waiting for the next pulse before it hits. Some bursts hit with extreme intensity for fractions of a second. Then the activity accelerates anyway. The timing stabilizes just long enough for prediction models to start updating around it. A sequence of bursts suddenly cuts off in the middle of an active monitoring run. The predicted bursts never appear. The screens remain fixed on the coordinates while the recording systems continue searching through empty incoming data. Hours pass. Nothing returns. The prediction windows stop matching the behavior after that. Observatories adjust schedules around recurrence estimates that keep failing in different ways. Dense clusters appear without warning, vanish completely, then return later under different timing from the exact same point in space. The maps stop looking chaotic long enough for people to breathe again. In 2017, astronomers finally traced the source to a small dwarf galaxy more than 3 billion light-years from Earth. Localization maps narrowed the bursts down to one dense region inside it. Simulations began reproducing the spikes with something physically familiar at the center of the model, a magnetar, a collapsed stellar remnant powerful enough to produce bursts of radio energy. FRB 1210-2 finally starts behaving like something observatories can track. The tracking displays become calmer after that. Timing charts flatten into cleaner intervals. Active windows start arriving close enough to prediction that observatories begin scheduling around them with growing confidence. One monitoring run stretches forward without major interruption. A burst arrives. Another follows near the expected interval. The next one lands close again. The source keeps returning year after year without losing intensity. For the first time, the bursts start looking less random and more cyclical. The galaxy maps stay fixed. The signal strength models hold together. Observers begin trusting the cycles enough to leave equipment running through longer windows without constant recalculation. Small timing drifts still appear inside the charts, though tiny offsets, a pulse arriving slightly early, another one delayed just enough to pull the intervals out of alignment again. The predictions still work often enough to keep the models alive. The timing just stops lining up cleanly every time. One burst arrives on time. Another arrives stretched. Two monitoring arrays display the same event side by side, but the structures no longer line up cleanly. A sharp spike on one screen appears fragmented on the other. Timing markers drift apart by fractions of a second, even though both systems are tracking the same burst. FRB 1210-2 stopped matching its own history. At first, the disagreement looks procedural calibration error, clock drift, instrument noise. The charts are rerun against archived recordings, while new bursts keep entering the catalogue anyway. The CHIME telescope begins adding more repeating fast radio bursts to observation records during this period. Many of them behave differently from the earlier patterns astronomers thought they understood. The comparisons keep getting stranger anyway. Previously successful prediction models stopped matching the new bursts. Burst intervals that once appeared stable now spread unevenly across the timing overlays. One sequence compresses tightly together. Another arrives stretched farther apart than expected. Some bursts split apart during arrival, as if parts of the signal reached Earth at different times. The source itself remains active. The source itself never stops transmitting. The bursts are still crossing billions of years of space to reach Earth-based instruments. The measurements stop agreeing with each other. One observation screen stays frozen on mismatched timing charts long after the burst sequence ends. The explanations keep multiplying after the signal survives them. Archived bursts replay beside newer detections while timing overlays stop lining up cleanly anymore. Magnetar activity, plasma distortion, interstellar scattering across impossible distances. Each explanation works for a while, then a newer burst arrives and breaks part of the pattern again. FRB 1210-2 keeps transmitting anyway. By the early 2020s, multiple confirmed repeating fast radio burst catalogues already existed. Some sources repeated for years without settling into stable long-term behavior. Others repeated under completely different timing patterns from the original source. The observations kept expanding faster than the agreement between them. A final burst enters the monitoring system, while older prediction windows remain open on the wrong intervals. The signal began its journey toward Earth before human civilization existed in its current form. Everything being observed now is already ancient by the time it arrives. The source could have shifted repeatedly before its first burst ever reached Earth. The monitoring screen remains active. New detections continue sliding across the frequency bands, while archived timing charts drift subtly out of alignment beside them. The sky itself never visibly changes. The instability exists inside the observation itself, inside the delay between distant events and human certainty. The bursts kept arriving long after the explanations stopped holding together.